Welcome to the sixth module of the Securium Bootcamp. This one is about Audit Techniques and Tools 101 and the central focus of this bootcamp on smart contract security auditing. In this module, we will cover the various technical and non-technical aspects of smart contract auditing, starting with the high-level view of what are audits and the entire context around that. We will then review the widely used tools in this space developed by teams from Trail of Bits, Consensus Diligence, and others. We will cover high-level aspects of these tools without getting too much into their operational or technical details, which is out of scope, and for which I would highly encourage you to install these tools and experiment with them during this module. Finally, we will review the audit process and the various aspects around that one will need to understand to become a smart contract security auditor. So let's dive in. Audit is an external security assessment of a project code base, in contrast to a review or assessment done internally by the project team itself. This external assessment, performed by a third party external to the project, is typically requested and paid for by the project team. It's meant to detect and report security issues with their underlying vulnerabilities, severity, difficulty, potential exploit scenarios, and recommended fixes. This includes both common security pitfalls and best practices, and also deeper application logic and economic vulnerabilities in the context of smart contracts. It may also provide subjective insights into code quality, documentation, and testing. The scope, depth, format of audit reports varies across auditing teams, but they generally cover these similar aspects. As for the audit scope, for Ethereum-based smart contract projects, the scope is typically restricted to the on-chain smart contract code, and sometimes includes the off-chain components that interact with the smart contracts as well. But for this module and the bootcamp as a whole, we are focusing only on smart contract security auditing. The goal of audits is to assess project code along with any associated specification and documentation, and alert the project team of potential security-related issues that need to be addressed to improve the security posture, decrease the attack surface, and mitigate risk. This typically happens before smart contracts are deployed on the mainnet before launch, so that vulnerabilities can be fixed and verified to avoid exposure. Along with the goals, we should also discuss what the non-goals of audits are. And this is perhaps even more important to level set the expectations. Audit is not a security warranty of bug-free code by any stretch of imagination. It is a best effort endeavor by trained security experts who are operating within reasonable constraints of time, understanding, expertise, and of course decidability. So just because a project has been audited does not mean that it will not have any vulnerabilities. It should certainly have fewer vulnerabilities than before the audit, assuming the reported vulnerabilities were fixed correctly. The constraints are also critical and real, especially that of time and understanding. For now, we can assume that most auditors are self-trained with some help from peers, with their experience in smart contract development or security in the Web 2 space being applied to Web 3. The expertise of auditors also significantly affects the effectiveness of audits, and we'll talk more about these in forthcoming slides. Who is the target for audits? Currently, security firms or teams execute audits for their clients who pay for their services. Audit engagements are therefore geared or targeted towards priorities of clients, that's the project owners and not project users or investors. The goal of audits, therefore, is not to alert potential project users of any inherent risk that may be evaluated during the audit. That is not the business or technical goal of audits. This is often a point of discussion when it comes to audit firms, their incentives and what they should be doing or not doing, and also in the context of where potential project users should look for unbiased security risk posture of the projects that they're interested in. Nevertheless, this is the current state of most audits today, where their clients are projects and not users or investors of such projects. Let's start with the fundamental question of why we even have audits in the Web3 space. The reasons are simple but multifold and mostly related to talent, market supply demand, and some unique characteristics of the Web3 space. Smart contract based projects do not have sufficient in-house Ethereum smart contract security expertise and presumably not even the time to perform internal security assessments given the pace of innovation in this space. Therefore, they rely on external experts who have the domain expertise in those areas. The reason most projects don't have that expertise is because the demand for it is orders of magnitude higher than the supply, which itself is because we are still very early in the Web3 life cycle. And this is also the biggest motivation for this bootcamp, as you know. Even if projects have some expertise in-house, given the risk and value at stake, they would still benefit from an unbiased external team with superior and either supplementary or complementary security skill sets that can review the assumptions, design, specification, and implementation of the project code base. So these aspects hopefully justify at a high level the need for security audits in the current landscape. Now, what are the types of audits? There aren't any standard categories, but we can consider some broad classifications based on the nature of such audits. Audits depend on the scope, nature, status of projects, and based on that, they generally fall into the following categories. We can think of new and repeat audits. New audits are for new projects that are just being launched for the first time. Repeat audits, on the other hand, are for existing projects that have had an audit or two before, but is being revised. There's a new version of this project coming up with new features or optimizations for which a repeat audit is being performed. Then there is a fix audit for reviewing the fixes made to the findings from a current or prior audit. Then we can think of a retainer audit where the audit is constantly reviewing project updates or providing guidance in a continuous manner instead of discrete engagements. And finally, we can think of incident audits, which review and exploit incident, root cause the incident, identify the underlying vulnerabilities that led to the incident, and propose fixes. This one is more of an incident response, unlike the traditional audits described above. There are also very likely other variants of these as well. But this should give a general idea of the types of audits which affect the scope and nature of engagements as well. The timeline or the time spent for audits depends on the scope, nature, status, and more importantly, the complexity of the project to be assessed and also the type of audit. This may vary from a few days for a fix or retainer audit to several weeks for a new, repeat, or instant audit that we discussed in the previous slide. This may even require months for projects with complex smart contracts with lots of external dependencies. The timeline should certainly depend on the anticipated value at risk in those smart contracts and their criticality, but that is generally hard to guess ahead of time. The timeline aspect is therefore a subjective one, and there aren't reasonable objective measures to make decisions. It's usually decided by simple metrics such as the number of files in that project, the lines of code, external dependencies on oracles or complex mathematical libraries, some measures of complexity of code or the application functionality in general, and even familiarity of the auditing team with such contracts from earlier engagements. The audit effort from a resources perspective typically involves more than one auditor simultaneously for getting independent, redundant, or supplementary complementary assessments of the project. The more than one approach is generally preferred to deal with any blind spots of individual auditors stemming from expertise, their experience, or even just luck. The cost of an audit is an often discussed and debated topic. It depends on the type and scope of audits and typically costs in the range of several thousands of dollars per week, depending on the complexity of the project, the market demand and supply for audits at that point in time, and certainly the strength and reputation of the auditing firm. The prerequisites for an audit are the things that should be factored in, discussed, agreed upon, and made available before an audit begins. This should typically include the following 10 things. Clear definition of the scope of the project to be assessed, typically in the form of a specific commit hash of the project files on a GitHub repository, which could be a public or a private repository if the project is still in stealth mode. The team behind the project, which could be public or anonymous and is engaged throughout this process. The specification of the project's design and architecture, which is critical to security, as we have discussed in earlier modules. The documentation of the project's implementation and associated business logic. And specifically from a security perspective, the trust and threat models and specific areas of concern from the project team itself. It should also include all prior testing done, tools used, and reports from any other audits completed. The timeline, effort, and cost payments for the specific engagement must also be agreed upon. The engagement dynamics or channels for questions, clarifications, findings, communication, and reports should also be agreed upon to prevent surprises. And finally, there should be single points of contact on both sides to make all this possible and seamless. Audits are generally considered as necessary, for now at least, for the reasons we have touched upon earlier. But audits are certainly not sufficient. They cannot guarantee zero vulnerabilities or exploits after the audit. They have limitations. This is because of three main reasons. The first one is residual risk. There is risk reduction from an audit, but residual risk exists because of several factors, such as the limited amount of audit time or effort, limited insights into project specification implementation, where in many cases there doesn't even exist a concrete written out specification, and the documentation or the implementation itself doubles as specification. Residual risk could come from limited security expertise in the new and fast evolving technologies, or the limited audit scope, where an audit may not cover all the contracts or all the latest versions or their dependencies making the deployed contracts different from the ones audited. Residual risk could arise from significant project complexity and limitations of automated and manual analysis. For all these reasons, and maybe more, audits cannot and should not guarantee fully secure code that is free from any vulnerabilities or potential exploits. Such an expectation is unreasonable, and any such positioning is misleading at best. Second, not all audits are equal. The quality of audits greatly depends on the expertise and experience of auditors, effort invested given the project complexity, quality, and tools and processes used. Getting an audit from a widely reputed security firm is not the same as getting it from someone else. This affects residual risk to a great degree. And third, audits provide only a project's security snapshot over a brief period of time. This is typically a few weeks or sometimes even less. However, smart contracts need to evolve over time to add new features, fix bugs, or even optimize. And this is sometimes done during or after an audit in code that is eventually deployed, which reduces some of the benefits of the prior audit done because the changes introduced could have vulnerabilities themselves. On the flip side, relying on audits after every change is also impractical. So these tensions between security and shipping unfortunately exist even in Web 3, similar to Web 2, but arguably have a more significant impact in Web 3 given the risk versus reward and other unique aspects of Web 3 that we have discussed earlier. So for these three broad reasons, audits are considered necessary but not sufficient by any means. Audits typically end with a detailed audit report provided by the audit firm to the project team. Projects sometimes publish such reports on their websites or GitHub repositories. Audit firms may also publish some of these with approval from the projects. Such reports include details of the scope, goals, effort, timeline, approach used for the audit, tools and techniques used, the findings summary, the vulnerability details, if any found, vulnerability classification as per the audit firm's categorization because there isn't yet a standardized categorization, vulnerability, severity, difficulty, likelihood as per OWASP or the firm's own rating and ranking, any potential exploit scenarios for the vulnerabilities which demonstrate how easy or hard it is for attackers, and almost always the suggested fixes for the vulnerabilities. They may also include less critical informational notes, recommendations, suggestions on programming or software engineering best practices which may lead to security issues in certain scenarios. Overall, an audit report is a comprehensive structured document that captures a lot of these aspects in different levels of detail. Most audits provide a report at the end, or there may even be interim reports shared as well, depending on the duration and complexity of the audit. And while the format, scope, and level of details of these reports differ across audit firms, they generally capture some or most of these categories of information. And we'll go into the details of each of these concepts in the forthcoming slides. The vulnerabilities found during the audit, if any, are typically classified into different categories, which make it helpful for the project team or even others to understand the nature of the vulnerability, the potential impact, severity, impacted project components, functionality, and exploit scenarios. And like we just discussed, there isn't yet a standardized categorization, and each audit firm uses its own. So for example, let's take a look at the classification used by trail of bits. There's access control, which is related to authorization of users and assessment of rights. Auditing and logging, related to auditing of actions, logging of problems. Authentication, related to the authentication of users in the context of the application. Configuration of servers, devices, or software, and in our case, the smart contracts or off-chain components. Cryptography, related to protecting the privacy or integrity of data. Data exposure, related to unintended exposure of sensitive information. Data validation, related to improper reliance on the structure or values of data. Denial of service or DOS, related to causing system failure or inaccessibility. Error reporting, related to reporting of error conditions. Patching, related to keeping software up to date using patches, in our case smart contracts that we have discussed earlier. Session management, related to identification of authenticated users. And finally, timing, which is related to race conditions, locking, or order of operations. And if none of these categories fit for the vulnerability, then it's typically categorized under undefined behavior that is triggered by the program because of such a vulnerability. We have broadly discussed these categories in the earlier modules on security. And other audit firms may use a slightly different classification, but usually there's a good overlap. According to OWASP, likelihood or difficulty, which are semantically opposite terms by the way, that's low likelihood is the equivalent of high difficulty. This is a rough measure of how likely or difficult this particular vulnerability is to be uncovered and exploited by the attacker. And OWASP proposes 3 likelihood levels of low, medium, and high. Some audit firms use OWASP, but others use their own terminology and ranking because OWASP does not apply very well to Web3 in general, given the nature of risks, vulnerabilities, and even extent of impact from their exploits. So Trail of Bits, for example, classifies every finding into 4 difficulty levels. First one is low. This means that the vulnerability may be easily exploited because public knowledge exists about this vulnerability type, as it is related to a common security pitfall or a missing best practice at a solidity or EVM level, which further implies that it may be easily exploited. The second is medium, which means that attackers typically need an in-depth knowledge of the complex system to exploit this vulnerability, and this may be something application specific that is related to its business logic and not a commonly seen or known solidity or EVM level vulnerability. The third one is high, which means that an attacker must have privileged insider access to the system, may need to know extremely complex technical details of that system, or must discover some other weakness in order to exploit this issue. This could imply that one of the trusted actors in the context of the application, such as one of the privileged roles, must be either malicious or compromised, and potentially even with some insider details about some design or implementation to exploit this vulnerability. And finally, there is the undetermined category, which means that the difficulty of exploit was not determined during the engagement of the audit. This could happen given the nature of the vulnerability in the context of the application, or even simply because the operational aspects of the audit engagement did not allow this to be determined. Irrespective of this subjective difficulty level determination, the relative classification across the 3 or 4 categories is what is more important. And this aspect should also be consistently applied to all the findings within the scope of the audit. The other aspect of vulnerabilities that is important to recognize is impact. And as per OWASP, the impact of a vulnerability estimates the magnitude of the technical and business impact on the system if the vulnerability were to be exploited. OWASP again proposes 3 levels of low, medium and high. But this again needs to be revisited for Web3 because the impact from smart contract vulnerabilities and their exploits is generally very high. And also the business or reputational aspects are very different in Web3 from a traditional Web2 sense. High impact is typically reserved for vulnerabilities causing loss of funds or locking of funds that may be triggered by any unauthorized user. Medium impact is reserved for vulnerabilities that affect the application in some significant way but do not immediately lead to loss of funds. Anything else is considered a low impact. These are again subjective in nature, but what matters more is that they make sense in a relative manner. So the high impact should be greater than a medium impact, should be greater than a low impact in some reasonable, justifiable way. And also this should be applied consistently across the audit. These difficulty and impact ratings again are different across different audit firms, with some of them being more stricter than others in classifying the vulnerabilities. And this aspect of impact is perhaps the most noticed and discussed aspect as reported for vulnerabilities in the audit reports. This is discussed and debated even between the audit firm and the project team, given the subjective nature of this classification, and something that gets paid a lot of attention even by the community at large when they are looking at high impact vulnerabilities reported in audits of the projects that they are interested in. According to OWASP, the likelihood and impact estimates are combined to calculate an overall severity for every risk, and this is done by figuring out if the likelihood and impact are low, medium or high, and then combining them into a 3x3 severity matrix. So with the notation of likelihood hyphen impact is equal to severity, the matrix looks like this. A low likelihood and a low impact results in a severity that is an informational note. A low likelihood, a medium impact results in a low severity. Low high results in high. Medium low results in low, and so on, as shown here. So this is what is recommended by OWASP, but different firms end up using different severity levels. TrailofBits, for example, does not use this OWASP recommendation and uses 5 severity levels instead. There's an informational severity where the issue does not pose an immediate risk but is relevant to security best practices or helps with defense in depth. There is a low severity where the risk is relatively small or is not a risk that the customer has indicated as being important. Medium risk, where individual users' information is at risk and exploitation would be bad for client's reputation and so on. There's a high severity where it affects a large number of users, it's very bad for the client's reputation and so on. And finally, there's an undetermined severity where the extent of this risk was not determined during the engagement. On the other hand, consensus diligence uses a different classification. It uses minor to indicate that the issues are subjective in nature, where there are typically suggestions around best practices or readability. Medium severity are for issues that are objective in nature but are not security vulnerabilities. And major severity is for issues that are security vulnerabilities that may not be directly exploitable but may require certain conditions in order to be exploited. And finally, there are critical severities where the issues are directly exploitable security vulnerabilities that absolutely need to be fixed. So as we can see, there are clearly different severity considerations across firms. But again, what matters more is the relative categorization, consistency, justification, and the clarity. A checklist for projects to get ready for an audit is helpful so that audit firms can assume some level of readiness from projects when audit starts. Trail of Bits, for example, recommends a checklist that has 3 broad categories: test, review, and document. For test, what is recommended is to enable and address every compiler warning, and to also increase the unit and feature test coverage. For reviews, what is recommended is for the project teams to perform an internal review to address common security pitfalls and best practices. For documentation, what is recommended is 1. To describe what your product does, who uses it, why, and how it delivers the functionality. Add comments about intended behavior in line with the code. Label and describe your tests and results, both positive and negative tests and results. 4. Include past reviews and any bugs found. 5. Document steps to create a build environment. 6. Document external dependencies. 7. Document build process, including the debugging and test environment. And finally, 8. Document the deployment process and its environment. And finally, having included the test, review, and document parts in a checklist, what is also more critical is to communicate all the above information in suitable ways to the audit firm before an audit, so that they have all this information and do not waste their valuable time in discussing, requesting, duplicating, or addressing these aspects. The analysis techniques used in audits involve a combination of different methods that are applied to the project code base along with any accompanying specification and documentation. Many are automated analysis performed with tools with some level of manual assistance. And there are generally 8 broad categories. There is specification analysis that is completely manual. There is documentation analysis that's also manual. There's software testing, which is automated. Static analysis, again automated. Fuzzing, an automated technique. Symbolic checking, that's also automated. And formal verification, that is automated with some level of manual assistance. And finally, there is manual analysis that is entirely manual. Let's discuss each of these categories in some detail. Specification, as we have discussed earlier, describes in detail the what and why aspects of the project and its components. Or in other words, what is the project supposed to do functionally as part of its design and architecture as stemming from the requirements. So from a security perspective, it specifies what the assets are, where they are held, who are the actors in this context, privileges of the actors, who is allowed to access what and when, trust relationships, threat model, potential attack vectors, scenarios, and mitigations. Analyzing the specification of a project provides auditors with the above details and lets them evaluate any assumptions made and identify any shortcomings. Very few smart contract projects have detailed specifications at their audit stage. At best, they have some documentation about what is implemented, and auditors end up spending a lot of time inferring specification from the documentation or implementation itself, which leaves them with less time for deeper vulnerability assessment.